We will deal with some numerical examples. These are from chapter 12. And the first problem that we're looking at is on page 327, and it is number 8. And to read the problem, calculate the energy in joules that would be released if a 60 kilogram person were converted entirely into energy. Energy and mass are equivalent according to Einstein's relationship E equals mc squared. In this case, the mass is given as 60 kilograms, and C is 3.0 times 10 to the 8, and it's squared, so it's 3.0 times 10 to the 8. So multiplying 60 by 3 by 3 gives you 540 times some powers of 10. Now 10 to the 8 times 10 to the 8 is equal to 10 to the 16th. So 10 to the 16th joules is the answer to the problem. 540 times 10 to the 16th joules. So the next problem that we're going to do is problem number 9. The sun's total energy output is 4 times 10 to the 26 watts. Now a watt is a joule a second, so this is the number of joules every second that the sun emits. Use the energy yield from the proton-proton chain to determine how many pp chain fusion cycles must be happening each second. So they want to know how many times each second do 4 pp atoms combine into 4 pp elements combine into 1 helium atom per second in the sun to produce the output that it does. And so they tell you that the sun's energy is at 4 times 10 to the 26 watts. So 4 times 10 to the 26 watts. And let's remind ourselves, is the sun. And let's remind ourselves that we're doing chapter 12, page 325, and number 9. Now, each pp interaction, as given by Astronomy by the numbers on page 313, will yield 4.3 times 10 to the minus 12 joules. So, 1 pp. So how many pp's are contained in 4 times 10 to the 28 if each one releases 4.3 times 10 to the minus 12? How many times does this divide into 4 times 10 to the 26? And the answer comes out to be approximately 10 to the 40 per second. And the reason for that is because 10 to the 26 over 10 to the minus 12 equals 10 to the 26 minus 12. This is from the fact that an over am is equal to a to the n minus m, and there is one minus sign from the equation, and there is one minus sign from the value of m, so this is equal to 10 to the 20 plus 12, 26 plus 12, and that should be 38. So, okay, so it's equal to 10 to the 38. And we'll make the correction right here. Instead of the 40, what we want is the 38. So we've answered that question. Now let's go to our third question. And I want to remind you that you can freeze the frame on any one of these and look at one board for as long as you want. The next question is question 10, which is a somewhat lengthy question, and it wasn't really expected that all of you would get this, at least not without some help. So to read the problem, estimate the lifetime of the sun, given some information. Assume that 10% of the sun's total mass is processed through the pp chain. That is, 10% of the sun's mass is in the core, and the core is the only place where the temperatures are hot enough for the pp chain to occur. So it's only the 10% of the sun's mass that is in the core that is candidate fuel and that will be burned in the lifetime of the sun. There is only so much hydrogen available in the core. And for each pp chain, 6.6793 times 10 to the minus 7 kilograms of mass is processed. That's roughly the amount of mass that there are in 4 protons, which combine to form helium, and they're no longer available for fuel. And is each time that this happens, then the amount of energy that is released, as we've used in the previous problem for the fusion of 4 protons into 1 helium, the amount of energy that's released is 4.3 times 10 to the minus 12. And again, that comes from page 313, Astronomy by the Numbers. And now assume that the sun's output is given as in table 1. And in table 1, we find that the sun's output is 4 times 10 to the 26 watts, which we've also used in the previous problem. So now how many years will the sun shine? So it's amazing that if we take these numbers that we know about and just do a little arithmetic, we can find the lifetime of the sun. So let's proceed with doing that. First we know, and so remind yourselves that we're doing chapter 12, page 326 now, number 10. So the total mass of the sun, and what we do is use the astronomy nomenclature here. A circle with a dot in it pertains to a solar property. So 1 solar mass is equal to 2 times 10 to the 30th kilograms. This is ascertained by using Kepler's third law and looking at the rate of the Earth going around it. We can ascertain the mass of the sun from the gravitational force. So we know that figure quite well. And we're also told that 10% of this is used. So 10% of this is going to be 2 times 10 to the 29 kilograms. We just take 10% of the total mass, reduce the power of 10 by 1. And each pp reaction uses 6.68 times 10 to the minus 7 kilogram. So each pp going into helium uses this much, 6.68 times 10 to the minus 27. So using these two numbers, we can find how many pp reactions are going to take place before 10% of the core is used up. So if we have 10% of the core available, which is 2 times 10 to the 29th kilogram, and each pp reaction uses 6.68 times 10 to the minus 27 kilograms, then we can see how many reactions we can get out of this 10% of the core by dividing the amount that each reaction uses into the total amount that we have available. So if we do that arithmetic, then 6.38 is going to go into, we're going to change this number in the top slightly so we get the arithmetic a little better, make it 20 times 10 to the 28th over 6.68 times 10 to the minus 27. Now 6.68 goes into 20 just about 3 times. Now let's do the powers of 10. 10 to the 28th over 10 to the minus 27 equals 10 to the 28th minus a minus 27. Therefore 10 to the 28th plus 27 equals 10 to the 55. And this comes about because a to the n over a to the m is equal to a to the n minus m, and there's one minus sign in the formula and another minus sign in the value. So this is the number of total pp reactions that are going to take place before the sun runs out of fuel. Now each pp reaction releases a certain amount of energy. So we have 3 times 10 to the 55th reactions, and each one releases 4.3 times 10 to the minus 12 joules. So this is the amount of joules that's going to be available when 10% of the core is totally converted into helium. So we do this arithmetic, 3 times 4.3 is right around 13. And now we have some powers of 10. And what we have is 10 to the 55 times 10 to the minus 12. Now a to the n times a to the m equals a to the n plus m. So this is equal to 10 to the 55 minus 12 equals 10 to the 43. So this is the total amount of joules that's going to be released in the burning of the entire 10% of the core. Now, the sun gives out the amount of joules each second as 4 times 10 to the 26. So if this is the total amount of joules that is released over the lifetime of the sun, and it gives out 4 times 10 to the 26 joules each second, if we divide the total amount of joules available by the total amount of joules it gives out each second, then we're going to get the total number of seconds that's available before this fuel gets consumed. So we get a 3.1 times 10 to the 17th power seconds. So this is the lifetime of the sun in seconds. So all we have to do is convert that to years. So we have 3.1 times 10 to the 17th. First thing we do is convert seconds to minutes. 1 minute is 60 seconds. Then we convert minutes to hours. 1 hour is 60 minutes. Then we convert hours to day. 1 day is 24 hours. And then we convert days to years. 1 year is 360 days. So we do arithmetic across the top. 3 times 10 to the 17th is still there. And we do the arithmetic across the bottom, and we produce 3.6 times 10 to the 7th. So if we allow for the fact that we're only doing an estimation, so we cancel out the 3 times 3 to the 6th, and we get 10 to the 17th over 10 to the 7th, which is equal to 10 to the 10th years. So because we arrived at 10 to the 17 over 10 to the 7 is equal to 10 to the 17 minus 7 equals 10 to the 10th. And therefore it is equal to 10 billion years. So we have calculated that the lifetime of the sun is 10 billion years. Now at this point we know from geological data on the Earth that our sun is already 5 billion years gone, so we know that it has 5 billion years yet to live.